Hello YouTube, this is Dazza the cameraman. Today is Tuesday, February 19th, 2019. That's New Zealand time. And once again, I'm very happy to have with me Astronomy Live. Welcome along, Astronomy Live.
Thank you once again for having me.
Thank you. And what is the time there at your location, please?
7:15 p.m. Eastern Time.
Okay, now we're doing another response to Mr. Thrive and Survive, who has just posted another video with his early results of their filming of the moon looking for rotation. And he has posted this video. Here is the moon evidence that doesn't exist, which is interesting. So he's presenting the interim evidence he claims, which shows some rotation. Now, he says that this video was filmed with an equatorial mount telescope, and we do actually see some rotation. Now, there's some interesting points to point out about using an equatorial mount telescope. It's not something that you just go and grab out of the back room and plonk down on the ground and point it at the sky. There are a few things that you need to do first before you actually start using the telescope. Would you like to give us an outline on that, please, Astronomy Live?
Sure. So basically, you can eyeball it. Sure, you can take your polar telescope, your equatorial mount, out of your closet, throw it out in the lawn. Take your magnetic compass out and say, okay, that's north in that general direction. I'm going to line my telescope north to be parallel to Earth's axis of rotation. And I'm at this latitude, and yeah, the mount's tilted at about this many degrees. I'm going to throw the telescope on there. That's good. I'm polar aligned. It's not that simple. That will not get you an accurate polar alignment. To do an accurate polar alignment, there's a couple different methods, all of which are dependent on being able to see the stars. If you look at the video they've posted, the first pictures appear to have the moon in the daytime sky, which begs the question, unless they have a permanently mounted telescope sitting in an observatory, which is, retained alignment over some period of time where it had been aligned at night, it begs the question, how did they have this thing polar aligned? Because it's blue skies. You didn't have any stars for reference. How could you possibly know that it's properly aligned? Sure, you could eyeball it. It would get you maybe to the right alignment within a few degrees, but a few degrees is not good enough when doing long exposure deep sky photography, or in this case, short exposure photography over a long period of time. If you want to avoid any hint of field rotation, you need to be very, very accurate with your polar alignment. And as I said, there's a few different methods to do this. One, the method I use most frequently is a little bit faster, a little less accurate actually, because it makes certain assumptions about the accuracy of your tracking mount. But I use what's called the iterative method, where you start with the telescope roughly aligned by eyeball. And let me tell you, it's never that good when you do it by eyeball. You can tell because you have to make a large number of corrections to get it accurate. You eyeball it, you get the telescope set up. I get my LX200 set to 0 declination and point it at the local meridian when I power it on. That's the home position. That's the position the telescope expects to be in when it's turned on. So I turn on the telescope and I tell the telescope's computer, move the gears to point the telescope at Polaris, the North Star. It does so. And then I physically move the mount both left and right and up and down in the tilt until Polaris is in the eyepiece and centered up. Then I tell the computer, okay, you found Polaris. Now move to another star, one far from Polaris, usually one that's close to the celestial equator, about 90 degrees at least from Polaris. So then it slews over there, and then I align the computer. I say, okay, I'm going to move the motors to find that star. Usually it's a little bit off in right ascension. Usually I'm pretty good about the tilt and the declination, but it tends to sometimes be a little bit off in right ascension by a few arc minutes out of the field of view. And so I get the star in the field of view, I center up the star, and I tell the computer, okay, you are now on that star. And then it's called the iterative method because you're using multiple iterations to successively and gradually dial in the accuracy of the alignment. So the next step, you go back to step one. You tell the telescope, slew to Polaris, slew to the North Star. It does so. The North Star will no longer be centered, although it was when I physically positioned it. I've now synced the computer, so the computer's got a better idea of where it is, where it's pointed at in the sky. But it's still, Polaris is not perfectly on the crosshairs anymore. So then I adjust the mount and move Polaris so that it's halfway to the crosshairs. Let me see if I can find a iterative alignment chart that can show you some pictograms, some diagrams here of what I'm talking about. Here we go, iterative method. He doesn't have any charts. Let's see if we can find one here with the, okay, that's just text. Yeah, there's, okay, well, that doesn't really show, but this, oh, wow, that's a really tiny picture. Yeah, never mind. Okay, well, I thought I could find one that had pictures, but it's all just text, and it's lengthy text. Actually, that in and of itself might be helpful here, just to give some people some idea of what's really involved here, because it's not as simple, like you said, of dragging your telescope out and throwing it on the lawn. So here's a description of the iterative process, which, as I said, this is the easy method. This is the, I'm going to cut corners here a little bit because I'm relying on the accuracy of the computer and the motors of the telescope, which are not perfectly accurate. They'll get you to within, you know, a few fractions of a degree, but it's not as perfect as some of the other methods, but it's very fast. So you first have to align the OTA, you know, you do all this, you set up your coordinates of the observing side of the computer, you set the time and date, you level the tripod, and then you go through this whole polar alignment process. The text here is very tiny. I'm going to try to blow this up a little bit so you guys can see it. So I'm sharing my screen here. And so it makes a few assumptions here about the accuracy of the telescope and everything. And you basically, like I said, as I described, you make mechanical adjustments, physically moving the mount successively, and then keypad adjustments where you're aligning the computer. And so step by step, when you align this with this process, you'll find that you on each step are making fewer and fewer, or smaller and smaller, corrections, both on aligning the computer and on aligning the mount, until they are in pretty close agreement. And at that point, you are polar aligned. But obviously, you need stars to do this. You can't do this without the stars. So that's one method. The other method is probably more popular, especially with really high-end astrophotography, is what they call the drift alignment method. And kind of like it sounds, you basically are allowing stars to drift and using that to align your mount based on how the star is drifting. So here's a quick picture here that shows you what you kind of see in the eyepiece. With a reticle eyepiece, you have these illuminated reticles that allow you to accurately center up a star. The star is out of focus in this example, but you're looking at how the star is drifting when it's positioned in various directions towards the western horizon, towards the eastern horizon, whatever it happens to be. And based on the direction it's drifting, you adjust the mount. So again, this is iterations, but instead of relying on the go-to accuracy of the mount, this doesn't require a mount that can actually move on its own to a target. You can do this with any equatorial mount that has a clock drive, which turns with the rotation of the Earth, whether it's computerized or not. And you can watch how the stars drift and gradually dial it in by adjusting the mount as needed based on the direction of the drift. So this process can take all night in some cases if you want to be really, really accurate with it and make very tiny adjustments. But you know, even at its best, it's still, you know, a process that takes a considerable amount of time, and again requires stars. So the third method I can think of to do polar alignment accurately is to, and this requires an assumption that the dials on your telescope are very accurate. If you position the telescope so that it's pointed at 90 degrees declination straight up towards the north celestial pole, and you rotate the whole telescope in right ascension. Let me show what an equatorial scope looks like, just so we can have some sense here of the axes I'm talking about. So here we go. This is a good diagram right here. So if you have an equatorial scope like this, and you're looking at, let me just want to see this image right here, a little bigger. There we go. So your scope should be pointed, in this case, this is a German equatorial mount, and so the polar axis is through this direction here. You should be pointing at the north celestial pole. If you position the telescope so that it should be pointing at that north celestial pole with 0 degrees of declination, and you are pointing in that direction, you can rotate the whole scope in the right ascension axis, spinning it around, and you should get concentric circles of the stars. You want to do this very slowly, of course, but you take a long exposure photograph through the telescope while you're rotating it in the right ascension axis. If you are polar aligned, those stars should be concentric with the north celestial pole. And you can check this using astrometry. So using astrometry.net, you can upload a photo of your star trails and see how well they align with the north celestial pole. You'll get a sense usually pretty quickly if you're accurate or if you're way off. So that's another way you can do that and sort of cheat the polar alignment using the magic of astrometry. But none of these methods are doable in the daytime. You just can't do that without seeing stars. You have to see stars to be able to accurately polar align them. And from what we've seen, the first pictures were taken during the day. So either they have a telescope that's permanently mounted on a pier, probably in an observatory dome of some type, or a roll-off shed observatory, where it can be stored day and night, and it was already polar aligned when they came out to it, or more likely, they dragged it out of their house, threw it on the lawn, and called that good enough, which it most certainly is not. You will get residual field rotation if you're not accurately polar aligned, which is why amateur astronomers go to all these steps in the first place. If it were as easy as pulling it out of the closet and throwing it on the lawn, do you think we would go to all this effort, writing out all these steps and executing all these steps in order to polar align it? Of course not. Of course not. We would take the easiest path. This is why I use the iterative method, because for me it's good enough, but it still requires viewing the stars. So I really should do a longer webcast next time. When I do my deep space webcasts, I tend to not show the part where I'm aligning the telescope because it's long and boring, but I think it leads to a general misperception in the public's eye of what it takes to do that kind of photography. It's not as simple as just throwing a telescope out on the lawn and going with it. It's a whole process to set it up and align it carefully every single time. And from all appearances, that doesn't seem to be the case here. So with that, I'll hand it back to Daza.
Right. Okay. Now we can actually scrutinize the video, of course, and look to see if there is some evidence that that the scope hasn't actually been set up correctly. Hopefully, I'm sharing my screen again now.
Yes.
So let's go back to the start where he started viewing the moon. As we said, it's in the daytime sky. Now, just to play devil's advocate here, I should point out that with some of the go-to controllers on the telescopes, you can do an alignment using the sun and I think possibly the moon as well. The SynScan remote, the SynScan controller that I've got on one of my telescopes will allow you to do alignment using the sun during the day.
Yes, that's true. Although I need to interject here. It is true. So you can do sort of a modified form of an iterative alignment using that kind of procedure, where you tell the telescope, move me to the moon or the sun, and then I'll position the mount to center that object up. Assuming you do that correctly, you'll be closer than you would be if you were straight out eyeballing it. But because you're locking onto an object that's moving through the sky and everything else, it's not necessarily going to be as accurate. Plus, you're omitting the whole second part of that iterative process, where you physically align it to the object that you have told the telescope to move to. In my case, it's usually Polaris. And then you move to a second star and bounce back and forth between that star and the first thing you aligned on, aligning the computer and aligning the mount successively in different steps. You can't do that if you're just aligning it on the sun or the moon. And so you've omitted the whole process, which allows the iterative method to be accurate enough to do many, a series of long exposures with no field rotation. When I did my lunar eclipse photography, for example, that's what I did. I did the iterative method, and that's the only reason that the moon is as stable as it is in my video.
Right. Okay, so let's have a look at the video again, and I'll play it again. And what do we notice as the video is playing? And I think he speeds it up. Here we go. So this is a time lapse. And of course, if the telescope is actually correctly aligned and set up, what wouldn't we see in this Astronomy Live?
Oh, man. Yeah, the moon's bouncing all over the place.
Exactly. All right. So that tells us straight away that this telescope is not correctly set up in the first place. If it was, then the moon would be perfectly centered and it wouldn't be moving around in the field of view as it is. We can see that there are corrections being made to this, and that wouldn't be necessary if the telescope was correctly aligned. Would you agree with that?
Yes, absolutely. I mean, you might have a situation where, for example, the telescope is set to track only at the sidereal rate, not at the lunar rate. I actually did that myself by mistake during the eclipse, but that drift is much smoother. It's a consistent direction, and it's not bouncing all over the place like this.
Yeah, this is bouncing around like a ping pong ball at times, isn't it? So
exactly.
There. That should not be.
Oof! Oh,
yeah.
Look at that! Oh man!
So
that's horrid.
That is
horrid.
That certainly shouldn't be happening if it was a correctly set up equatorial mount, properly aligned with the celestial pole and so forth. Now we get into this next section, and I'll put the sound on for this, where Mr. Thrive and Survive is presenting a bit of an analysis, and he is showing some apparent rotation. Now we've already covered off about field rotation and what causes that, and Mr. Thrive and Survive, of course, is saying, well, here is a video of the moon that has been taken on an equatorial mount telescope, which, as we've just stated, is clearly not been set up correctly. So he goes through these images to make a comparison. So we'll just have a listen to a bit of that. I'll just turn on the sound here. And let me know in the chat if you can't hear the sound properly.
What I did was here, I took still shots from the video you just saw at different times of the night. And everything you're going to see here is before meridian crossing. This is, again, it started in daylight. Right now, what I did was, let me get to a darker picture so you can see what I did. There is a white crater that sticks right out here in the middle. I used that because it's the only one I could see visibly when I was doing the daytime shots, just to make sure we were matching. And I took an angle up to the Sea of Crises right here, and in fact, this is the one I used as my base. So I use that. I'll make it so you can just barely see that little teeny speck of white in that crater right there, and then right through the Sea of Crises. And I took this line and just duplicated it. The exact same size and angle is throughout the whole thing here that you're going to see. So at 3 p.m., I know it's a little bit hard to see here, and this is as large as I can make it. Maybe in post-production I'll make this larger. You can see the right up in here is the Sea of Crises, and the line is actually going through the left, let's say 1/4 of it, or maybe even 1/10 of it. Most of the Sea of Crises is to the right. Again, this is roughly 3 p.m. The first shot we got through the clouds. And I don't know if you can tell here, but the very next shot is showing some slight rotation, actually. And they'll say that's too small to even measure. So, okay, maybe we don't have any. But now we're not on the left of the Sea of Crises anymore. We're right through the dead center of it. We're getting counterclockwise rotation, which would actually be the opposite of what we should see in the field rotation. So anyway, here we have this. And it's a pretty steady until all of a sudden here. And this jump between here and here occurred, let me see if I can get the time here, between 7:19 and 7:26, roughly. So in a less than 10-minute period, we got this much of a change, suddenly counterclockwise. Then what happens? And we're still nowhere near meridian crossing. We have the exact same thing 45, 50 minutes later. Each one of these photos is roughly 45 and 50 minutes apart, roughly.
Now, I'm just going to pause it here and point out something very curious in this image. Now, I like to be a bit more charitable than some people. Instead of accusing people of outright lying, I like to try and get to the truth and, you know, give people the benefit of the doubt. Instead of saying that they're lying, that they've made a mistake, that they're confused or whatever. But I'm a little bit troubled about what I'm seeing in this image, because if any of you are familiar with using Photoshop and other photo editing programs, if I'm not mistaken, then this could actually be a rotation tool, the handles for the rotation tool. So that troubles me a little bit as to why that is in that image, and maybe there is a perfectly good explanation for that. But clearly, Mr. Thrive and Survive is pointing out some rotation. And as we've already covered in this video, the equatorial mount telescope that was used for these images was clearly not set up correctly. Otherwise, the moon would not be bouncing around like a ping pong ball in the video over time. But there is another aspect that we have not covered. And sure, an equatorial mount telescope will actually cancel out field rotation, which is the rotation that we see as we follow an object across the sky, explained in my previous videos. The other aspect that we have to account for, of course, is the tilt of the orbital plane of the moon. So maybe you could speak into that, Astronomy Live.
Sure. So the moon is orbiting over the course of the night around the Earth, and its orbit is not at 0 degrees inclination. And so it will appear to undergo some degree of motion, even if you have a perfectly polar aligned telescope. Field rotation is just one part of that aspect of calculating the moon's the apparent orientation of the moon. If you want to calculate the apparent orientation of the moon's limb, you also need to calculate what we call the position angle in astronomy. So let me pull up a book here. I've actually got this formula listed in a book I have on Google Books. While I do that, also let me share with you a calculator I've got here that will tell you about how much field rotation you can expect over a given period of time for a given amount of mount misalignment. So I'm going to be generous here and assume that they got the alignment within about 10 degrees. I'm usually worse than that when I eyeball it, just when I'm roughly starting out. Maybe they even did better than that. We could even assume that they got it within, let's say 5 degrees here. So let's say even 5 degrees. That's pretty good for eyeballing it. If they got it within 5 degrees, you're looking at an angular size of the moon of about ½ a degree from one end to the other. So that's what I've set as the guide star angle here. And so if with a focal length, I don't know what their focal length of their camera is. I'm just going to assume about 300 millimeters and a time of about 3 hours. Moon's declination last night was about 19½ degrees. We get a field rotation angle, or a field rotation amount of 190, almost 191 microns. Now, what is that? So that's the rotation of the optical field of view. To convert this to number of pixels, you have to know the physical size of the pixels on the CCD. In my case, with the Canon T5i, that's about 18 microns, so that's more than 10 pixels of field rotation. So it would show up quite noticeably in my camera, even at that focal length. If you expand the focal length, I believe that will go up. Yeah, that'll go up if you expand the focal length. So I don't know how much zoom they were using or what the focal length was, but very quickly you run into unacceptable amounts of field rotation when you're trying to observe an object over hours of time and you're hoping to get 0 field rotation, no field rotation. It should be pointed out, I think, that according to the video that they showed, although there is some degree of rotation visible there, it's not nearly the kind of rotation that we normally see in videos that show field rotation, where the moon has flipped 180 degrees from the start of the video to the end, which is entirely possible. That's entirely normal and consistent with field rotation from an altitude azimuth perspective. So even if we take the video at face value, right away we can say that they've eliminated almost all of the apparent motion of the moon by polar aligning, if that's really what's going on here. But as you said, that's not the only thing to consider. There's also the position of the moon relative to the sun, and you can actually use that angle to calculate what the position angle of the moon's bright limb should be. Let me switch screens that I'm sharing here so I can show this handy dandy book. Okay, so this is Practical Astronomy with Your Calculator by Peter Duffett Smith. But anyway, first of all, you have to calculate the position angle, this right here, this whole nasty mess. And really all this is all you need for calculating that is the declination and right ascension of the sun and the moon. And so you have the cosine of the declination of the sun times the sine of the right ascension of the sun minus the right ascension of the moon divided by all this cosine declination moon, sine declination sun minus sine declination moon, sine cosine declination sun, cosine right ascension sun minus right ascension moon. Okay, that's a mouthful, but the bottom line is at the end of the day, you'll get an angle out of that, which you have to take that into account if you are looking for the apparent position and apparent orientation of the moon such that the moon's terminator is vertical in your view. You have to consider what angle the moon is at relative to the sun in the sky. What is that position angle? Because the moon, of course, is being illuminated by the sun. And so that illuminated limb will always point towards the sun. This fancy formula right here allows you to calculate that position angle.
I noticed the description under the video by Mr. Thrive and Survive, and of course, looking at the phases of the moon, we can see that it's a couple of days old. It wasn't taken last night. And he says in the description, here is the moon evidence that doesn't exist, evidence in capitals. The video contains footage of the waxing moon as observed from Chandler, Arizona on, hang on a minute, 9/16/2019. Well, that doesn't make sense, does it? Must be a typo. So that I'm assuming that must be February 16th, 2019, with a typo in the date.
Yeah, absolutely.
So now that's interesting because the video that I uploaded last night just before I went to bed demonstrated or simulated the expected field rotation of the moon as seen from Phoenix, Arizona on February 16th, 2019. So we'll come back to that in just a minute. So you've got something there at Astronomy Live?
Yeah, basically this X symbol from that equation that we were just looking at is this X symbol on this diagram, and you can see a line pointing from the center of the moon north. This is on the equatorial grid, and you can see that even on the equatorial grid, we're not expecting that the moon's orientation is perfectly vertical at all times here, because you have to take into account the sun and how the sun is illuminating the moon and the angle between those two. So to find that angle, you look at this diagram here. The X represents an angle from that vertical line north on the equatorial grid to a line perpendicular to the moon's terminator. And so if you run that calculation, as we saw earlier, like the example calculation, it came out as 70 degrees. So it's not always going to be 90 degrees where it would be perfectly aligned with the equatorial grid. But if you take that into account, you can find the moon's apparent orientation, the apparent orientation of the moon's bright limb. Now, one important point here, one caveat I should put out here, is that at a full moon, if the moon is full, at the full phase, that terminator is going to be either on the top or the bottom of the moon. So the calculation won't make any sense in terms of the features on the moon, the craters and so forth. Most of the month it will, but when it hits full moon or new moon, this breaks down and ceases to make any sense.
Right. Now, this is why Astronomy Live does the maths and I do the simple stuff.
All right, I got to take off, but thanks for having me on.
Yep, thank you, Astronomy Live, once again. It's been a pleasure. Okay, and I'll carry on here. I'll just go back to sharing my screen with you with Starry Night. So here is Starry Night, February 16th, 2019. My location is set to Phoenix, Arizona, United States. It is 3:23 p.m. and we've got the moon just coming up over the horizon there. Now, this is basically the same as I presented in my video last night. So I'll zoom in on the moon. You can see I've got the pole sticks selected and the equator. Now, I've got the time step set to 1 minute, so I'm going to run this forward, and you'll notice that the moon seems to tilt anti-clockwise. It's tilting this way to start with, and then it slows down again, and I can see that transit across the meridian is at 10:23. So I'm just going to pause it. You see it's suddenly done a sudden flip because we've just gone past the meridian. I'll just bring that back so you can see the meridian. That's that bold line there. That is the line between due north and due south, and it is the point where the moon is at its highest point in the sky as it crosses the meridian. That is when you're seeing the most of the rotation as we're approaching the meridian transit. Okay, so I'll run that forward again, and you can see it's tilted completely the other way. And comparing this to what we see in Mr. Thrive and Survive's video, we can obviously see that there is considerably more rotation if we're not using an equatorial mount telescope than what we see in the video that he presented on an equatorial mount telescope. Now, if you've joined us late in this, we also looked at the fact that it was clear that that equatorial mount telescope was not set up correctly, because in the video the moon was bouncing all around like a ping pong ball, which wouldn't happen if the telescope was set up correctly. Okay, now I'm going to address something else, and I'll make another shorter video on this. We can see that the moon is actually rotating back this way again, which is a bit of a curious sort of problem. So I'm going to address what's going on, that the main rotation that we see is due to the field rotation, as we've explained, but we've also got the secondary field rotation. I'm bringing this backwards now to moonrise, which was about 3 p.m. So it's 3:30. And there is our horizon there. Now in this view, we've focused on the moon. We've got the moon centered in our photo frame, the yellow box there. But what I'm going to do now is I'm going to give you an all sky view of the moon. Okay. So, and I've got to put the north at the bottom. So if you imagine that this is a map, but it's a map of the sky, and sky maps always have, if you're looking at them flat, you'll notice that east and west is actually on the wrong side, because they're intended to be held basically above your head, with north at the bottom and south at the top, and then east is on your right and west is on your left, which would be correct. And you can see that we've got the meridian line here running from north to south. And again, I've got the daylight turned off, which is why the sun is showing over there. And what I'm going to do now is I'm going to turn on the local path of the moon as it's crossing the sky. And we'll run this forward again. And so we're tracing out the path of the moon as it crosses the sky. And already we can see what's actually causing this secondary rotation in the opposite direction. We're actually passing across the sky more than 180 degrees of angle, because the moon is rising sort of in the east-northeast, and it's setting in the west-northwest. Okay. Let me just bring that back again. I'll just do it a different way this time. Okay, so this time I'm going to step forward with hours, and that should keep the track up for me, because it can only display so many points at a time. Okay, so you can see that the moon was actually rising over the horizon down here in the east-northeast. And then it crossed over into the southern half of the sky, and then it came back into the northern half of the sky before setting in the west-northwest. Now, the fact that it's actually crossed the east-west line causes that secondary rotation. And if we actually check the points in time where the moon actually crosses the east-west line, we see it matches the rotation that we see in the first video that I did. And I intend to upload a shorter video explaining that in better detail than what I can do here in the live feed. So that is why we're seeing the moon rocking in two different directions during that time lapse. Not only in a real time lapse taken through a camera, but also in the Starry Night simulation. So that is what we're seeing there. So I'm just going to finish by recapping Mr. Thrive and Survive's video there, and just pointing out once again that as he played that video, what we saw was the moon bouncing around in the sky like a ping pong ball, once we can see it through the clouds. And as Astronomy Live and I have both discussed in this Hangout, this would not be happening if the telescope was correctly aligned. A correctly aligned telescope will track an object perfectly in the sky. I mean, that is the whole point of tracking and having an equatorial mount telescope, so that there is no rotation, no field rotation, and your object remains centered in your field of view. I mean, it gets worse as we go on. You can see the moon is bouncing all over the place, and a number of serious corrections are having to be made to keep the moon in view. I think that Mr. Thrive and Survive did mention about battery changes and so on, so I have to throw that in there to be fair. But even between times of filming and making adjustments and so forth, we see that the moon is actually moving all over the place. It's drifting very, very badly here. So I'm not sure what's going on. Maybe the battery ran out on the telescope tracking motor, and maybe it wasn't tracking any longer. So Mr. Thrive and Survive, you have some questions to ask of the person who sent the video to you, assuming that you didn't film it yourself. And properly, I don't want to sound like a stuck record, but a properly aligned telescope will keep the moon properly within center without it drifting all over the place and bouncing around like this. So with that said, I think I'll wrap this up. There will be more on this. I will be uploading some other shorter videos in response to Mr. Thrive and Survive. And also, again, I would like to say to Mr. Thrive and Survive that I've now sent 2 messages to you via your People for People website. I've taken screenshots of those messages. In your Hangout last night, you acknowledged that you had seen my message but had not replied. I'm still waiting to get an email reply from you, and I'm starting to wonder if you are trying to avoid me. I mean, you're saying all the right things in your public Hangouts about working with people and, you know, allowing people to have different opinions and so on, but to do so respectfully. And that is always my intention. But one thing that I don't like is when people close down discussion, particularly when they block people and delete comments and try and stifle discussion. Now, I've invited you to talk with me directly. I don't mind if that's privately or in a public Hangout, but I'd be happy to share my screen with you as I'm doing here to answer your questions and to respond to any objections that you might have about the explanations that you are given. You know, I've got the astronomy software. The other thing that I was going to point out too, just quickly, let's go back to Starry Night, is that I can actually change the orientation. This is local standard, assuming that we're using a alt azimuth mount telescope or camera. I can change this to equatorial or ecliptic or galactic or supergalactic. So if we change it to equatorial, and let's go back to the time of moonrise. Okay, so this is the view, and let's just find the moon there. The centering on the moon. So what I'm going to do here, just before we go, is we're going to check what sort of rotation we would see. And remember that Astronomy Live and I did touch on the fact that the orbital, the tilt of the moon's orbital plane also needs to be taken into some account. But this will certainly cancel out the field rotation, which is the main amount of rotation that we see. So once again, I'll run this forward, and it looks pretty stable to me. And, you know, we do have to cover a number of hours. I'm not sure if I'm seeing a little bit of tilt there. But either way, my point is that I can simulate either an alt-az mount telescope or camera, or an equatorial mount or whatever. So Mr. Thrive and Survive, you know, it would be nice if you'd come and talk to me directly and we can have a proper discussion. And as I say, I'll answer your questions and respond to any objections that you might have. So thank you for joining me in the Hangout, everyone. Thank you for your comments in the chat, and we'll see you again next time.